Good afternoon, PreCal students. Hope you've had an awesome day. I had some issues with the first video that I uploaded, so it didn't have any sound, and so I have to re-upload the video, so I got to record the entire thing. So just be patient with this, and hopefully we can get through it, and everything will be just fine. What we're going to do today is starting 7.2, graphs of complex numbers. We introduced complex numbers last lesson, and we're just going to expand on it a little bit and actually graph it. It's nothing more than graphing some coordinates on a Cartesian plane. It's not called the Cartesian plane, it's called the polar plane or polar coordinate system, and that's what we're going to be looking at today. So without further ado, let's just jump straight into the lesson. Real numbers are graphed on a number line. We already know that. You guys learned back in pre-algebra how to draw a number line, and if I said graph x equals 2, you'd put a dot on 2 on the x-axis where the number line would be located. Then you got to algebra 1, and you started to graph two number lines in relation to each other. You graphed an x number line and a y number line, and we put those together and we made what we call the Cartesian plane. So today we're going to be talking about complex numbers graphed on a complex plane. And literally what happens here is you're going to have a complex plane, looks just like an x and y chart, nothing different. But notice, if hopefully I can get this to work here, if I can right on top of this, let's see here, there we go. Maybe I could do it this way. If you guys notice on this particular graph, you have the real number system, and you have I, which stands for the imaginary number. And we've already talked about the complex number from last lesson, a plus bi. Again, I'm sorry I have to write with my finger here, my Apple Pencil I don't have with me. So a plus bi is the complex form, where a is the real number and b is the imaginary number. So this graph here is just showing a relationship between the two. So you have the real axis and you have the imaginary axis, and that coordinate there, that black dot there, is literally 4. You guys can also think of it, some students like to think of this as the x and this as the y, because here you have x is 4 and here you have y is 6, and you plot that point, which is the black dot that they have there. So it's basically the same thing. Think of it as an x and y chart, a Cartesian plane. That may help you understand it a little bit how it works. Now the textbook leaves out a couple of very important components to this, so I'm going to fill in some pieces as we go. But the first term that it's going to talk about goes through here, talks about this: the absolute value of a complex number is the distance from the origin of the graph to the complex number. The previous slide I had up there, if you put a dot on the origin and you connected it to the dot, which was 4 and plus 6i, that gives you the absolute value, the distance I should say, between the two. And when you do that, the r there becomes the radius, if you want to think about it like that, radius of the unit circle. And it's equivalent to, the radius is actually equal to a plus bi. So when you take the absolute value of a plus bi, that's going to give you the square root of a squared plus b squared. And again, the text leaves a lot of very important information out here. And let me see if I can kind of fill in some of the pieces here. Let's see here. So basically what this is talking about, again, you'll have to apologize for the rough drawing here. But if we have a complex plane like we have right here, an x and y chart, you can think of it like that. When I connected the origin to the dot that was out here, literally what I can do here is, first, this distance here is the r distance. And it's actually called the modulus, and I'm going to mention that in just a second. There's a formula for it. But if I were to draw the triangle, and you always do this, to the x-axis, and I were to say, hey, this is a right triangle, this is distance A, this is distance B, and to help you guys understand how that corresponds, remember, this is the real number line, and this is the imaginary number line. So when we have the complex number a plus bi, that's where we get this a and b from. So literally I could use the Pythagorean theorem and say a squared plus b squared equals r squared, and then what they do is they just take the square root of both sides, and that's how they get this equation right here. That the absolute value of a plus bi is equal to the square root of a squared plus b squared, derived through trigonometry. So that leads us to another term here that we definitely need to know. The absolute value of a complex number is called the modulus. Some textbooks call it the resultant. Some people call it the hypotenuse. You guys may remember the resultant from physics class with vector notation, and we're actually going to talk about that a little bit. But that's kind of what it's talking about. It has a specific name called the modulus. The argument is the angle that is formed by the positive real axis and with the terminal ray by passing through the graph of the complex number. So this seems really confusing, but let me show you this picture and it'll help you understand. You guys notice here you got a modulus drawn. It starts at the origin. So you see this point right here starts right there in the middle, and then this is the polar coordinate that it's talking about, the a plus bi, that dot there that the arrow points to would be the modulus. So you can use the Pythagorean theorem once again to figure out the length of the modulus. And then you have theta here. This is very important. Theta here is called the argument, and it's the distance or the angle from 0 degrees to the hypotenuse, also called the modulus. So that's very important to understand that it's theta, and that's what's called the argument. Notice that the triangle is always drawn to the x-axis, and the argument is always drawn from the x-axis to the resultant. So very important to make sure you guys understand those distinctions there. All right, so theta is the argument, r is the modulus, and if you wanted to solve for theta, you have b and you have a. Because remember, that's going to be a complex number, like the previous slides had 4 plus 6i. 4 would be the a, and 6, the piece with the I, would be, coefficient with the I should say, would be the b. So you have tangent of theta equals b over a. So if I wanted to look for theta, I would just take the inverse of both sides. And that's what they do. You take the inverse of tangent, they cancel, and you get theta by itself. And that's going to be equal to tangent of -1 of b over a. So that's how you figure out what the argument actually measures. And this is what you guys are going to have to be doing today. So here's example 1. Find the modulus of 3 plus 3i. Well, we have a formula for this. If you take the absolute value of that, it's going to be equal to the square root of a squared plus b squared. And that's where they get that from. Again, to help you guys understand what's going on here, again, it's based on the complex number system or the complex plane. You have x is 3, or the real number is 3, 1, 2, 3, and then you have the imaginary number, which is 3i. So I'm going to go up 3, because again, the y-axis is the I-axis, and this is the real number. Man, that's terrible. This is the real number line there. So literally, you're plotting those points, and you would put the dot here. That would be the coordinate, 3 plus 3i. You connect it to the center, or the origin, I should say. Then you always draw the triangle to the x-axis. So if this is 3, and if this is 3 and this is 3, then we can use the Pythagorean theorem to solve for r. This formula here just takes all that work out of it. And you don't have to draw it out because you actually can write that down as the definition of a modulus and write the equation down there. The absolute value of a plus bi is going to be equal to the square root of a squared plus b squared. So you literally can just plug it in. I like showing this to you though right here, this concept, because that's what's important to understand how they actually derive the formula and how they plug in the variables in order to figure it out. In fact, the next lesson, 7.3, you're going to be working a lot with this, and having a good understanding of it now will help you with that. So they simplify that to get the square root of 18, and then they simplify square roots of 18 and get 3 square roots of 2. Okay, good. Moving along here, for a specific complex number, there is a unique modulus. So if you give a complex number, again, a plus bi, that format, there's going to be one modulus that fits that. However, there are an infinite number of arguments associated with that complex number. Okay, so let me explain this to you guys. It's not super difficult. Again, I'm drawing my complex plane here. Let's say we'll make it simple. Let's say I'm back in this first quadrant. That's the length of the modulus. There's going to be a point out here that corresponds with that as a complex number, the a plus bi. Now that makes sense. There's only one line that justifies that point. And again, it's called a modulus. However, the second part, an infinite number of arguments exists, and this will make sense if you want to think about it like this. You guys understand again, The argument is the distance from 0 degrees to the modulus. And that's going to be equal to an angle. I'm just going to say, for sake, that that angle is 30 degrees, okay? I'll make it a simple number. 30 degrees is the measure of that angle. But what happens if I keep going all the way around and I keep going around and I come back here? I make a full circle around. Well, that measurement would be 360 degrees plus the 30 degrees, because the full circle would be the 360, so that would give me 390. But this is what's interesting. Even though you go 390 degrees, you're right back to the same modulus. So it's the same hypotenuse, if you want to think about it like that, or the same radius if you want to think of it in terms of the unit circle. But you could actually keep going around. I could go one more time around and add 360 more to that. I'm still back to the same modulus. So that's what it's talking about when it says it has an infinite a number of arguments, because you can keep going around and around and around. But that radius, or the hypotenuse, or also called the modulus, is going to be the same exact number. It's not going to change. The value in interval notation is 0 to 2 pi. Remember, the bracket there means it includes the point, so that includes 0 degrees. And the 2 pi with the parentheses there means it goes all the way to that point, which would be 2 pi, but it doesn't include it. So you don't make a full circle, because, again, if we graphed it out, again, let me get my picture back up here. If you graphed it out, you would go all the way from 0 all the way around, but we wouldn't touch the 360 degrees or the 2 pi. So it gets to it and approaches it, doesn't touch it, but that's kind of the reference point. So, but the value is usually written as in interval notation of 0 and 2 pi. Sometimes textbooks will write it like this: 0 is less than equal to theta. Again, you have to I apologize for the sloppiness of this, but it's less than 360. Or it could be less than 2 pi. It's the same thing depending if it's radians or degrees. So this is just the interval notation, but this is the domain of that particular function oftentimes. So they have to limit it, because if they didn't, like you guys see on the right side with that, the resultant with all those circles around it, it could keep going forever. So there's always going to be a domain listed on there for that. Okay, equal complex numbers. There's a couple things here. Two complex numbers are equal if two things are true. One, their moduli are equal. So the hypotenuse has to be equal. It has to be exactly the same. And their arguments differ by an integral of multiples of 2 pi. Again, going back to the picture or sketch and what I had up here on the screen a while ago, this is the resultant, or the modulus. And then if I go from here to here, it's a certain degree. It could be anything. But if I keep going all the way around, it's going to be a factor of 2 pi times whatever that was. So literally, if the first piece I drew from here to here, let's just make it easy. One we know is pi over 6. We know that's 30 degrees. If I multiply that times 2 pi, that will give me 2 pi over 6, multiples of 2 pi. So it has to be, I don't really want to multiply it by that, but it'll be just simply divisible by the 2 pi. And if you divide it by the 2 pi, you'll end up getting the pi over 6. So whatever full revolution, I guess, would be, what, 2 pi? So it's basically plus 2 pi, not times 2 pi, because it's a multiple of 2 pi. So you add that, 2 pi is 12 over 6 pi, which would give you 13 pi over 6. That's what it would be if it went all the way around like I have there in purple. So this would be the purple degree, or radian, if that's what it was referring to. So that's how you determine if they're equal or not. All right, so almost done here. Moving right along. A complex number can be represented graphically by vectors. A vector has both a direction and magnitude. You guys already know that. And probably you also remember that vectors can be written with the vector notation. Looks like a greater than or less than, like 2 and -5. That would be a vector notation. This would be the x, and this would be the y. But if we think about it in our imaginary number system with a complex coordinate system, this would be the real number, and this would be the imaginary number. Or, again, not to be confusing, if you had the general form, a plus bi, the 2 would be the a, and the b would be the -5. So you're going to also work with vector notation with these. So you always have an initial point. The initial point is always the origin, and then you have a terminal point. That's where it ends. So that's kind of how this works. The magnitude of a vector is the absolute value of the complex number that it represents. Hopefully, y'all understand this is the same definition, almost exactly the same as the modulus. So the magnitude of a vector is always going to be equal to the modulus. A vector in standard position has its initial point at the origin itself. So again, the starting point is always going to be the origin, the 0, 0 point. Equal vectors. Okay, here we go. Vectors are equal if they have the same magnitude in the same direction. So the hypotenuse has to be the same, and they have to be going in the same direction. That's the definition of equal vectors. Two vectors can have different locations on the coordinate plane and still be equal. The reason this is true is if I draw this picture for you, and again, some of you guys that are taking physics already know this. If I have a vector going this direction, I could also have a vector in the third quadrant going this direction. And if it's the same angle, if the related angle here, also called the argument, if that's equal, it's talking about the same vector. Sometimes this will be a negative r. So it may say -2, and this may say 2. That's actually talking about the same exact vector. It's just written in a different quadrant with that negative number as the hypotenuse. Direction can be determined from the slope of the vector and the direction that the arrow is pointing. So the direction is simply which way it's going, and you guys understand slope. If I had the slope of the particular vector, particularly this one that I have here up here already drawn for you guys, if I were to draw a triangle here, and this was 3 and this was 2 or whatever, or that wouldn't exist. Obviously it wouldn't work. Maybe a 1 and square roots of 3, something like this. The slope of that would actually help you understand what direction it's going to be pointing. Also, the big factor there is the signs on these. If this is, this obviously would be a positive here, and this would be a positive. But in this triangle down here, this would be a negative, and this would be a negative. So that's kind of what it's referring to there. Okay. The way this textbook chooses the right vector notation is they're going to use the letter U, and it's going to be bold. So anytime you ever see that bold U on a problem, it's like it's pretty emphasized pretty drastically. That's how that indicates that it's a vector. And again, we've already talked about vector notation. That's the way it's written. However, with you guys on your homework, you cannot bold a U, so you'll have to do the vector notation like this, with a half arrow on top of a U. These two things are equivalent, and that's also equivalent to this. So just remember, when you're writing these on your homework, don't bold a U. You'll need to draw a U with the half arrow to indicate that it's a vector. Okay, so find the complex number associated with the given vector. You guys see the vector there has a magnitude of 16, and the direction is 5 pi over 6. So r is equal to 16, and here's the tricky part. This is what I don't care for. They say theta is 5 pi over 6, and it is 5 pi over 6. But remember, when we're calculating all this stuff, and this is where they kind of just randomly think that you guys can figure this stuff out and know that that's what the answer is. I don't like that at all. The way I would recommend to do this, because you guys don't have things memorized, there's two ways to do it. One, go ahead and make your triangle here. So you draw that straight down. You want the argument. That's what's important. Now you got two options here. Option one is to convert the 5 pi over 6 to degrees, so we can figure out what the argument is. That's equivalent to 150 degrees. So I know that the argument would have to be 30, because that blue line, I'll emphasize it right here, that angle right there is 150, which means that's 30 degrees. Another way you could have done this, some students prefer to do it this way. How far is it from here all the way to here? Well, that would be pi. So I could say pi minus 5/6 pi, and that would give me that argument as well. Regardless of how you do it, if you did that, you would get pi over 6, which you guys hopefully again have memorized. Pi over 6 is equal to 30 degrees. So here's what I would do on this problem. I would draw my triangle. I would say, again, it's going to look really small here, sorry. That's 30 degrees. And this is going to be B, and this is going to be A. Again, A always goes with a real number, and B always goes with the imaginary number. So here I would simply use trigonometry, guys. And you will end up getting decimals. The textbook on this problem, the reason they get 8 and 8 squares of 3 is because they actually use a special triangle. They notice that that's 30 degrees, so I could use my 30, 60, 90 right triangle, and that's perfectly fine. If you guys like to do that, that's perfectly fine. The only problem is, the only time we could do that is when it's either a quadrantal angle, like on an axis itself using a unit circle, or we could do it if it was a 30, 60, 90 triangle or a 45, 45 triangle. Well, obviously, y'all understand there's many more vectors that exist that are not those angles, where you would have to use trigonometry. So you may want to get accustomed to using it. It's really up to you at this point with this particular one. A is right next to 30, so it's the adjacent, and I have 16, which is the hypotenuse. So that the way I would set that up is I would say adjacent and hypotenuse is cosine. So I'd say cosine of 30 degrees is equal to A over 16. Again, you cross multiply and you're going to get your answer for A. When you do that, if I'm not mistaken, let's try it real quick here. Let me get my calculator going. I think it's, let's see here. If I were to say 30, the cosine of 30, and then times 16, it gives me 13.85. So that's what A would measure. And if you did solve for B, B is opposite, so that's going to be sine. So sine of 30 will equal opposite, which is B over 16. Again, you punch all that in your calculator, and I'll do that real quick. Sine of that is 0.5 times the 16, and that's where we get the 8 from. So we get 8 for this, and for A, you get the square root of 8 squares of 3. Now here's where you got to be careful. Your signs matter. Where these pieces are located on the triangle make a difference on your answer. Because you guys notice B is on the positive, so that's going to be a positive, but A is on the negative side. So when we write it as our answer, we have to negate the value of A. So I'll go ahead and continue here. And you see they got B is equal to 8 and A is equal to negative 8 squares of 3. When you use trig, you just get 8 squares of 3 or your special triangles. But you got to remember it's on the negative side. As you guys again can see, this is the negative sign here. Let me erase some of this. This is the negative side and this is the positive side. So that's the signs that are going to be included. And A is the real number, so that's going to go first, and then plus BI, the second number, that goes second. So that's how you rewrote this in the complex number. That's the complex number, okay? So again, trigonometry will be very helpful. All right, your assignment, I've already given your substitute the assignment, so go ahead and make sure you complete that. I think you'll do fine. It's not super difficult. You'll have a couple of vector notations to figure out, and then you'll also have some converting to rectangular coordinate system. But I think you guys will do just fine on this. Not a super hard lesson, but I think if you'll, again, have your formulas written down, understand the modulus is nothing more than the hypotenuse of the triangle that you could construct, and also that the argument is the angle that's drawn to the x-axis. Those are the key components to the lesson. So hopefully you'll do well on the assignment, and I look forward to seeing you guys later this week.